I'm going to talk about the project that I work on at Livermore. This is mostly a visualization sort of presentation, but it's a new kind of visualization, or I guess relatively new. The project's been around for 2 years. And the visualizations have to do with performance data. The team is me, Martin, and Timo sort of got together and started this team, and we ended up hiring Abhinav Batele, who I guess everyone here is familiar with because he came from your group. And now we're working also with the University of Utah, California Davis, and Clemson, as well as some students at the various places. So the motivation for this project is that, I mean, there's a lot of performance data that people collect from parallel applications. And not all of it is terribly intuitive. So I mean, if you take your standard MPI tool, like Vampire Trace or something that most people use, you get some sort of mess that looks like this, where this axis is processes and this is functions. So these different colors are different functions being called over time. And then this black mess is all the messages that went back and forth between the processes. And so then everyone looks at that and goes, and then occasionally they figure out what was wrong with their program and go on with their lives. But this sort of view doesn't really scale, and it's very hard to make any sense of once you get past, I think this is 64 processes over here that I'm showing. And then the other types of measurements that people collect are things like performance counters from their hardware. So this down here is showing the floating point counts on each process ID in an MPI application running on 256 cores. And so this domain down here is not so intuitive. If you look at this a little more closely, you can see that there's some variance between the different process IDs, but the process ID really has not a lot to do with what the application itself is doing. And so beyond that, you can see that there's some sort of load balance in the computation. There's not much you can glean from this. And so the sort of fundamental idea behind the stuff I'm going to show today is that one way to make this more useful is to show all of these types of data in the domain where the application developers think about them. And so if you think about a fluid dynamic simulation, what I'm showing here is some sort of, so this is a shock that comes in from the top of this domain, and then it drives this jet down the left-hand side of the simulation here. So you can think of some sort of shock coming in the top, and then this comes down this side of the simulation, and there's a bunch of vorticity down here. And this is this is the same 256 process simulation. But this axis right here, this is, I think, 8 processes wide, and this is 32 processes. And it's just your standard contiguous domain decomposition. But if you take that same floating point data and you project it onto the domain where the application is doing something, then it makes a lot more sense, because you can actually see that, okay, there's higher floating point counts where the simulation is doing more complicated things. So over on the left where that jet is traveling, you can see that there's higher floating point counts. Down where there's a lot of vorticity in the simulation, there are higher floating point counts. And around the edges where there are boundary conditions and less neighbor data to compute on, you can see less floating point instructions. And so here, red is high and the whitish color is low. And then we plotted the same thing for cache misses for this simulation, and we got something similar. And so we said, you can see that the cache misses are correlated with what's going on in the simulation. So we said, well, okay, we should extend this idea to try to project between lots of different data domains, so that we can actually visualize the measurements we're taking in the domain that their root cause came from. We divided up this simulation space into your physical simulation data, which is up here. So this is what your application is doing. This is some sort of fluid dynamics again, maybe with features in some sort of grid or a mesh. Some sort of performance data in a network topology. So this is your physical machine. So I'm showing a torus here with cores embedded in a torus network. And this is sort of the space where you usually take your measurements. You're measuring something about the hardware, and so it has to do with points in this space. And then your parallel applications will typically have some kind of communication pattern. So say it's a stencil. Then this might be the logical topology of your application, but you may want to embed this. This may be embedded in some weird way in the network. And we can project in all sorts of different ways between these different domains. So what I'm going to talk about today is a few of the different visualizations that we've done. The first one is more about this hardware to application mapping, where we take floating point instructions and other types of measurements and actually project them into application space. The second one is some communication visualization in an AMR code that does load balance and how we debugged a performance problem using an intuitive visualization. And then I'm going to talk about the network visualization tool we've built, and then I'm going to give a couple sneak peeks at future directions of what we're working on right now. So if we take that simulation that I just showed you and expand it out to more than just one time step, this is the same domain, but I'm showing you, I think, 9 time steps now. If I look at the aluminum distribution and the velocity distribution, you can definitely see the shock wave sort of propagating through the domain. These are the same floating point operations that I showed before. And then we ran this on a NUMA machine and tried to figure out, we tried to plot the cache misses on the same domain. This time we saw something pretty interesting. Part of these cache misses are actually correlated to what the application is doing. So part of them actually follow the shock wave. But then there's these bright spots here where you're getting more cache misses on particular processes and not on others. And whereas the floating point instructions themselves are actually pretty clean, because floating point instructions are mostly generated by the application, and so you wouldn't expect strange other sources of data to be generating floating point instructions. And so we said, well, what's the matter with these L1 misses? It turns out that if you take that simulation and you look at how it's decomposed over the actual nodes and sockets on the machine that it's running on, this is an Opteron machine where each node is a 4x4 core NUMA. And it turns out that down at the bottom here, those bright spots are actually it's the same core on every node in the simulation. And what we think that is the MPI runtime actually coming in and shoving data out the NIC, because that's the core that's closest to the NIC on those machines. And so it's interesting that you can actually see these kinds of artifacts in the performance data that you measure. So we did a little more exploration here. And so this is the same data now shown with a sort of monochrome color map. And here's the L1 cache misses, and again, the floating point operations. And so you can see here that, yes, these are still pretty clean. And the cache misses are showing these bright spots. So I said, well, okay, what if we take the bright spots out? So I averaged the bright spots I replaced the bright spots with the average of their neighbors. So just replace them with a halo to kind of filter that out. And what you get is something that's much more correlated with the application domain. But you can still kind of see this checkerboard pattern here. And what we think that is it's the shared memory communication that goes on before you actually shove something out the NIC. So it's the aggregation traffic that's going on the node as you push the data out. And so we said, well, we could do some more with this data. It kind of makes sense that if you have more floating point operations, that you'll also have more cache operations. So this is, in some sense, this isn't very surprising. If you're doing more computation, then you're going to just get more cache misses. So, but what if we actually divide these things out to get kind of a rough proxy for efficiency? So if I plot the L1 misses per FP operation, then I see something pretty interesting here too. One thing that you notice is that kind of checkerboard pattern from the shared memory communication really comes out at you, because it's stuff that doesn't really correspond to application activity that's polluting your cache. So you can really see that very strongly. The other thing that was surprising to us is that you can actually still see for this simulation some correlation to the shock wave. So that tells you that there's some sort of maybe minor inefficiency on the shock wave where the application is doing something more complicated. And so what we're working on now is taking this technique and trying to generalize it. These plots were generated by just putting calipers around a time step in the application. So when you start the time step, you start your counters, and when you stop it, you finish your counters. So we didn't really have to do much to get this data, but it gave us something interesting. We'd like to be able to decompose things like this into some sort of visual explanation of what your how your code is working. What are the different performance characteristics? And so you could think of this as like, I don't know, like a Fourier decomposition or something, or dividing something up into a sum of basis vectors, where one of the vectors is, this is the stuff that is correlated with your simulation. We suspect that this stuff is actual application behavior. This other stuff is correlated with maybe some component of the MPI runtime according to the profile data that we took. And we want to basically take each of these sort of fields, because we have the same data or the same program being executed on many processors at once with different data. And we want to tie them to different components of the runtime, the operating system, and even the application. So that's what we're working on right now. So stepping back from the hardware to application projection for a minute, I'm going to show some projections on the communication domain. And so this is not projecting on the application, but it's or not the application physics data itself, but we're going to project onto the communication patterns of the application to sort of understand a performance problem. And so SAMRAI is an AMR package that's used at Livermore by a number of codes. And essentially, if you're not familiar with AMR, what you're doing is you're solving a grid, kind of like what you did before, but you have a hierarchy of these grids. And so there are multiple levels, and each of the levels is progressively more refined. And so the idea is that you refine where you need to do, where there's more interesting stuff going on, where you need more resolution. And so this gives you an inherent load balance problem, because if you refine on some processors, then there's less work on the other processors where you didn't refine, and you have to balance it. And what we were seeing in SAMRAI is that this is a plot of the time spent by the simulations. We scaled up to 128,000 cores on BlueGene P. The total of the solving and adaptation was going up linearly. The adaptation phase, which is each of these lines is included in the one before it. So basically, solving and adaptation includes adaptation, and adaptation includes load balance. We saw that the load balance phase was really taking up the most time here. It wasn't scaling very well as we got up to closer and closer to 128,000 cores. And so we went and tried to plot the time spent in that load balancing phase. And what we saw was this. There's 3 phases to load balancing. Abhinav, what are the phases of load balancing for first? We need to send load to who?
Figure out the average load.
Yes.
And then decide how much load we're going to send up or down the tree.
Right.
The second one is actually doing the load migrations.
Yes.
And the third one is children waiting for the loads to arrive.
Yes. Okay. And so what we saw was that most of the time, it looked like most of the time was actually being spent in phase 3 of the load balancer, which isn't where the load is moved. And so if you aggregate these kinds of measurements across all of your processors, you'll see something like this, where you're emphasizing the wrong phase. When we plotted this out for every MPI rank, we saw something more like this, where the actual time was being spent in phase 1, and the only reason that you see processors in phase 3, or the reason that the aggregate looks like it's in phase 3 is because all of those guys are waiting on the guys in phase 1. And so, this told us that there was something wrong with phase 1, but it still didn't quite get to the root of the problem. And it was only when we started to plot the actual tree network that they use for load balancing that we understood what was going on. So the way this works is that SAMRAI it routes the patches that it needs to move from process to process through a tree network like this. And we thought, well, okay, so maybe there's an imbalance. Maybe there's a really big imbalance in the number of patches on the different processors. And so what this is showing is the whole tree overlay network. This is embedded in some sort of torus, by the way, with the load on each process colored on the processes. And then on the links, we're showing the amount of traffic that goes over each of the links and in what direction it goes in. But there's no particular imbalance in the load distribution here. There's definitely processes that are more refined than others, but there's not really much of an imbalance there. But then we plotted the time spent. This is actually time spent waiting for traffic, or for boxes. And we saw that one entire subtree over here was spending a lot of time waiting, and that this corresponded to where we're actually sending the most data. And so it turns out that what's really going on here is that if you turn a tree upside down, it's a funnel. And so this thing has a bisection bandwidth of 1 right through the middle of the tree network. Now, this isn't physics data that's being routed through here. And so the idea was that the metadata is so small that it's not really going to matter when we route it through this network. And that was true up to a point, but once we start to get to 128K processors, there gets to be an awful lot of metadata. And so what's really happening here is there's something like a 9% underload over here, and each of these trees is about 3% overloaded. And so when that happens, you're basically forcing that 9% to all flow through the root, and so you get a linear scaling bottleneck. And that's what you're seeing over here. We plotted the max number of boxes sent down the tree by any one link. And so you can see that grows linearly with the number of processors. And so just by visualizing it this way, we were able to see the problem because you can actually see the communication dependencies of the network that the application developers are using. And these are just timings for each processor that we're actually visualizing. And so, this visualization is actually getting kind of busy. you can see that if we were to do this for 128,000 processors, I think this is like 16K, but this is 1024. If we took this up to 100,000 processors, this would get pretty busy too. So we said, well, okay, what if we just show the part of the tree that matters and sort of coalesce the leaves? And so we built a visualization where you can actually see the links in the center, but the leaves are sort of averaged out into these arcs. And you can see the traffic over here. You can see exactly where the problem is because all the load still goes through one link. But the problem with this is that now what if the problem happens to be in another area of the network? So we adapted this visualization to show, to scale the size of the subtrees based on sort of some criteria of interest. And so in this case, we did how much traffic is on the links in a particular subtree. But what that's showing is that the subtree where all the weighting is happening is sort of amplified. We gave it half the radians here. And the other three subtrees are sort of collapsed because we don't care as much about them. And so we think that this will scale out to lots of cores and be able to show us problems in different areas of at least tree networks. And so we did not rewrite the load balancer for this code, but we were able to mitigate the problem by trading off a little bit of load imbalance from granularity for a lot less metadata. And so what we did was we increased the box size that SAMRAI used. And by doing that, we were able to reduce the max amount of metadata that flowed through any link. And so we got something like a 22% reduction in time on 65K cores, and you can imagine that would scale out to 128K. Let's see. And so if we do manage to fix the problem with the load balancer here, and it seems like the latest version is scaling pretty well on BlueGeneQ, then we think that the next problem is going to be topology mapping. And so we've tried to do some of our hardware to app mapping for this AMR code. And so this is a little more complicated than what we did before for Miranda. With Miranda, the fluid dynamic simulation, that had a contiguous domain decomposition where each process had its own chunk of the domain. With SAMRAI, we've actually gone in and put in some code to map the hop counts for patches to their neighbors to the particular patches. And so what this is showing, you really can't see it here. This is always a problem. But there's a red spot here and a red spot here. And if this was a brighter screen, then it might come across better. But what we're showing is the max hops to any particular neighbor. And so when this code does latency-bound computations, these are going to be the spots that limit performance. Is the spots where a patch actually has to communicate with something very far away on the physical network to get its job done. So the third thing I'm going to show is a network visualization tool called Boxfish, where we're actually sort of playing around with some of the counters that are available on the BlueGene machines. We can take per node counts and project them onto actual nodes in a network visualization. This is for a 3D torus. We're not quite sure yet how we're going to do a 5D torus like on BlueGeneQ. And we can also plot per link counters, which BlueGene has, and project them onto the links of the application. And we've got facilities for plotting MPI communicators, which is what you're seeing here. So this is for a code that does, there's a laser sort of traveling in the Z direction here, and the application is subdivided into communicating planes. Each of these planes does an alt-all, or it does a 2D alt-all. And we're interested in sort of in the balance between the communicators and also the speed with which we can get these alt-alls done. And we've played around a little bit with task mapping, so that's what's being shown down here, is how these communicators were tilted. One of the things that we've done to sort of improve this view and to show the load balance on communication links for bandwidth communication is if you notice here, a lot of these links are occluded. So it's very hard to see what the link traffic is, what's really going on inside the torus in this view. It's good for the nodes because they really stand out here, but the links are kind of underemphasized. So we've created this 2D view of the torus that lets you sort of look down one axis and take out 1/3 of the links and show the traffic so that you can see all the links at once. And so this is your traditional 3D projection here. We've kind of flattened that so you can actually see the load balance across different links. Other types of visualizations we can do with Boxfish include visualizing job layout on the Cray machines. This is a pretty new one that Abhinav is working on for supercomputing. So if you're seeing highly variable performance on some Cray machine where your job got another job put smack in the middle of it, we can actually show that here. And I'll do a quick demo of that. Let's see. I've got it over here. Yeah. with Boxfish, we've tried to really emphasize this idea of projection. And so what we've got here is this is the tool. This is sort of the workspace area over here. And down here, we've got a bunch of different views. And the idea is that, if there is a projection available, if the tool knows how to map the data from your run to one of these domains, like say it's the application domain or maybe it's a network, then you can just drag the data on there and it will do one of the logical projections that it has available to it. So what you do to visualize this job ID data is you could take your 3D view of the torus here and drop it over here, and it's not showing anything just yet. But if I then take the job ID from each of the nodes in my job, and I say I'm going to drop that on the nodes, I want to project the job ID onto the nodes, then what I get is this. So let's see, is this the right one? This may not be the right window yeah, and so then you can actually see the nodes being colored by the actual job ID from the Cray machine. And this isn't the greatest view. I think the rendering in the other view was probably better. I'm in the other branch. I'm in the wrong branch. So maybe I'll try it over. I've opened the wrong one with the wrong branch. Let's see. No, I'm on the master over here. I think I'm on the right branch. So, yeah, this is the SC13 branch. So I'm going to try it one more time and see if I get the picture that I saw in the presentation. My demo has gone awry. I dropped this 3D view in over here, and I just dropped the job ID onto the nodes. I should get, no, I get the same thing. So the supercomputing 13 branch is not quite stable yet, as you might imagine, since the deadline's like next week. But anyway, it is showing the job ID plotted on the nodes. Go back to the presentation over here. So that's about it for the tools we've developed so far. We've got sort of a summary view for showing load balance. I'm not going to get into the details of that. But for future directions, one of the things that we're pretty interested in is increasing the granularity with which we can do this sort of hardware to application domain projection. And so one of the newest things we've been doing is playing with these precise event-based sampling counters on the new Intel chips. And if you're not familiar with these, if you're familiar with PAPI, what PAPI does is you start a counter, and say you start the floating point instruction counter, you start the cache miss counter. Every time a cache miss occurs, that counter gets incremented, and the result is basically how many cache misses happened since I started the counter. With PEBS, it's a little different. You can actually sample instructions, and so you say, I'm going to sample all of my load instructions, and so I want you to record information about the latency, the level of cache that the last load instruction went to, and store that in a buffer. And so you can go and read this buffer every once in a while and see sort of a sampling of your loads, what their latencies were, and what level of cache they went to. And so we said, well, okay, if we've got the memory operands of the loads, then we could actually map them back to an application data structure and show cache behavior on the actual data structure itself. And so one of the sort of traditional examples of cache optimization is a blocked matrix multiply. So what we're showing here is an Ivy Bridge chip and two views of a matrix multiply. One of these is with 512 by 512 blocks, and one of them is with 256 by 256 blocks. And what you can see here is the latency of the sampled load instructions that happened on each of these elements of this 1000 by 1000 matrix. And so for the 512 by 512, it turns out for this cache configuration, I think 256 by 256 is optimal. So you don't see very many bright spots over here. And it's kind of hard to see clear lines in the way that the cache is laid out. But over here, if you do 512 by 512 blocks, then you can see that sort of halfway through your cache, you have a really big memory latency when you go to do the fetch of stuff that's been pushed out of cache, and the processor goes to prefetch everything else. And so this is the time that it takes for that memory operation to come back. We've also been sort of playing around with this on actual physics meshes. And so this is Lulesh, which is a shock hydro code. It's an open benchmark that Livermore has released. We tried to do this cache mapping back to all the elements of the Lulesh mesh. And so what we saw was that pretty frequently you can definitely see that there are lots of cache misses on the element where all the energy originates in this shock wave. And we don't really quite know how to interpret that yet, but I thought I'd show you these pictures because we just generated them. And then finally, to get back to my first slide, we're working on cleaning up MPI traces so that, or even communication traces. You could probably do this with Charm too, where to make it so that this is more understandable. And so this is what you typically get with an MPI trace. You can see that it's very hard to tell what phase of the code you're actually in each of these phases in the MPI trace. And that's because this is plotted in real time. So you actually have to see the weight, and it sort of distorts your view of the communication that's going on. What we've done is we've come up with this sort of time-stepped view of that of this trace, where we look at the communication operations and we sort of divide them up into different phases of communication. And so the interesting thing about this is for this multi-grid simulation, you can actually see the different exchanges happen, and they're sort of nicely lined up in the way that you would logically think about the communication, as opposed to the way that you would look at, as opposed to having to untangle the mess at the top. And so you might say, well, okay, you can't see the timing information anymore here, but what we're doing is we're coloring each of these sort of time steps for each of the processors, or communication steps, by its lateness. And so that's if each of these messages was able to be received on sort of the next time step, or whichever time step it was supposed to be received on, then they would all look blue. But what you can see up here is that the top part of this communication trace is sort of getting progressively later, and that actually the lateness is contagious. It actually sort of, when this block of messages gets sent down to the bottom of this sort of butterfly-looking network for multi-grid, then you can see that these guys get late too. And so it's easier to think about the way that you coded up your program if you look at it like this, and to see the actual lateness of the message, than it is to try to sift through a giant trace over time. And if you visualize it this way, you may be able to go and find patterns in there that you can kind of extract and sort of summarize most of the trace and look at just the interesting part. So that's the kind of stuff we're working on. Livermore, that's all I've got for today. So I guess I'll open it up for questions.
What's the lateness with respect to?
I think it's with respect to the time step where you were supposed to receive the message. So like if this message were received, one time step later in real time, I think you pick an arbitrary time step, then it's how much after that it was actually received. How much after the time you expected it. I believe so. Yeah. Okay.
So I can imagine some nice integrations with Charm++ to get some visualizations of, say, how maybe things are migrating and other information you can gather from like charts. So any thoughts?
Well, we've got, I think, 4 of Sanjay's students for the summer, so it seems like a right opportunity for such an integration.
Okay.
Yeah. Any other questions? Yeah.
So you said it may be difficult to generalize one of the views that you showed 4 or 5 dimension torus's.
Well, so we could show slices. So I was showing the.
Why not just show essentially 4-dimensional? You have a 4-dimensional view right there. If you assume that the top one and the bottom one are kind of the two. Basically, your dimension goes from top to bottom, right? And then you get to torus.
So we can do that, and we have actually had some really bitter arguments about whether that's the right thing to do.
Okay.
I think there's some website you can go to where there's like this 5D Rubik's Cube that you can play with, and if you try it, and you try to do a rotation in this 5D Rubik's Cube, it's very hard to tell. It's doing what you're suggesting. It's showing several of these lower dimensional spaces in order to emulate a larger one. But if you actually do a rotation operation on the Rubik's Cube, or if you actually move something, it's damn near impossible to tell what went where and what the neighbor relationships are in that dimension that you spread over the subspaces. And so I think that would be useful, but we're not 100% sure whether we really want to expose users to that or whether it's going to confuse them more. Yes.
How do you see these tools adapting to perks or any networks?
Sorry?
How do you see these tools adapting to perks or any networks, or are these meant for them?
So,
Can you repeat the question?
So the question was, how do I see these tools adapting to networks with different topologies like perks and areas, which are sort of dragonfly networks? I'm not 100% sure. I mean, we've started looking at that as part of Avano's project to look at network congestion. And actually, I think, I'm not sure that understanding the performance on those networks is really quite such the topological relationship that you have here. Like there's no clear neighbor relationship. And what you really want to know is what's the congestion like. And so Aries is doing a bunch of really interesting dynamic stuff under the hood to sort of to move the traffic around. And I think we'd have to really understand that before we started talking about what kind of visualizations we could do for it. Any other questions?
Have you tried to play network traffic?
Yeah, so actually that was one of my other demos before. Yeah, I can do that last one. This is the master branch. This one. This is not going to be an exciting visualization. I think this is just a sample data set that we made. But yeah, if you were to take this packet value here, it's the packet counters on the different links on the network, and you can drag it onto the links in the view, then we can actually color the links by the amount of traffic on them too. And I think this is some kind of all-to-all inside the torus, because you can see more dense traffic in the middle, and nothing on the wraparound links over here. But yeah, we've tried visualizing some of this.
So in this code you are using genuine content?
This is BlueJean. So this is a contiguous. Yeah, this is a BGP counter. And it's aggregate over a period of time, and so we're trying to figure out how to really get time in there. And again, like it all gets back to understanding congestion better, because yeah, we can visualize how many packets went over a particular link, and you can have some understanding of what's going on in the network. But you can't really see where the traffic actually contended for the same links or the same NICs on the node. So we're working on that. All right.